Hi everybody, today we're going to talk about systems of inequalities. So here's just a general overview of how to graph a system of inequalities. First, you're going to graph each individual inequality, just remembering that if you see greater than or greater than or equal to, that means to shade above your line. If you see less than or less than or equal to, you shade below your line. And if you just see greater than or less than, so with no equal to sign, you actually graph with a dotted line. And if you see an or equal to sign, you graph with just a normal solid line. And then your solution set of the system is where the shaded regions of each individual inequality overlap. So you're going to shade that in, and that's actually going to be your answer. You're going to have a graphical solution, but you're also going to find the coordinates of the vertices of the solution set. So you're essentially then going to solve the system as a system of equations to find where the lines intersect. So let's give one of these a try. So here they want us to graph the solution set and then label the vertices. So we're going to graph these three lines, just a really rough sketch as well. So I'm going to rewrite that first equation as y is greater than x minus 2, just so it's easier to graph. It's in slope intercept. And then I can see here I have a vertical line, and this will actually mean to shade to the right of it, because in terms of x, it's going to be right or left, and then we have a horizontal line. So let's graph those. Okay, so I'm going to graph the first one in red, the second one in blue, and the third one in green. So let's start with the green. This is going to be a solid line at 3. And then we would shade everything below. Our second one is going to be a vertical line at -2. And we would shade everything to the right of that. And then our linear equation is going to have a y-intercept of 2 and a slope of 1. So it's going to look something like this. More or less, but that's just a very rough sketch. So you see I didn't even label any of my my x or y axis. So now I'm going to think about where would all of this overlap. So remember, it's everything below the green, everything to the right of blue, and everything above the red. So you can visualize that it's just going to be in this actually triangular area right here. So this is our solution set. Now, the other thing we're going to need to do is we're going to actually need to figure out what are those three coordinates that bound our solution set. So this first one is going to be pretty easy. It's just where the blue and the green collide. So we know that this is just going to be at the coordinate -2, 3, because we actually know the x and the y values. So this coordinate down here is going to be where the red and the blue collide. So I'm going to use these two equations. So I'm actually going to substitute x equals -2 right here. So I can say -2 minus y equals 2. So -y equals 4. So y is going to equal -4. And I'm going to write that as a coordinate, and then that would be this coordinate right here. And then this coordinate is going to be where the green and the red collide. So I'm going to substitute y equals 3 into our first equation. So we have x minus 3 equals 2. So x is going to be 5. So that's going to be 5, 3. And there you have it. So that's our solution set. Once again, that shaded area is our solution set, and then it's your job to find those three coordinates, and it's really just solving the systems algebraically. All right, so go ahead and pause the video and give this problem a try. Okay, so let's have a look. So you can see that we have two linear equations, one with a positive slope, one with a negative slope, and those actually intersect at the same y-intercept. And then we have a vertical line at 2. So if we're shading below the green and above the red and blue, this little triangular area is going to be our solution set, and then we have the three coordinates. All right, let's try another one. Now we have a quadratic equation to graph. So I'm going to rewrite that one again. So as y is greater than or equal to x squared minus 1. And I'm going to rewrite this one also into slope-intercept form. So I can see that my first equation is going to be a parabola that has, and once again, I'm going to graph this one in blue, red, and this one in blue. So it's a parabola that has a vertex at 0, -1, and then it's just an upward facing parabola. So it's going to look something like this, just a really rough sketch. And for this inequality, we would shade everything above. Now our second one has a slope of 1 and a y-intercept of 1. So it would look something like this. And that one we would shade everything below. So everything above the red and below the blue that overlaps would be in this region right here. So this is our solution set. So now we're going to need to find these two coordinates. So maybe you can tell if you have a nice graph, if you've graphed it really accurately, but we can solve it algebraically. So now we're imagining these are equations. Let's use substitution. Let's set this equal to this since they're both equal to y. So we can say x squared minus 1 equals x plus 1, and now we can solve by setting our equation equal to 0. So we have x equals 2, and we have x equals -1, which we can go in and we can substitute into either of our equations. So I'll substitute it right there. So we have y equals 2 plus 1, so y equals 3. And then we have y equals -1 plus 1, so y equals 0. So we have the coordinate -1, 0, which does match our graph. So it's a nice way to check to make sure that everything kind of fits together. There you have it. All right, so go ahead and pause the video and give this problem a try. All right, so this one you might have noticed that it's going to be a sideways parabola. We have x equals y squared. And so we're going to have to kind of do a little critical thinking and interpret this. So since it says x is greater than, that's going to mean shading everything to the right. Here we're shading everything below our blue line, so this shaded region is our solution set. And then to solve this one, I use substitution. I know that y is equal to -x plus 2, so I substituted it right here. So I have -x plus 2 squared. Now we just have a quadratic equation, so which is why we have two solutions. So we have the solution 4, -2, and the solution 1, 1, which does match up nicely with our graph. Okay, so now we're going to look at an example that has a system with no solutions, which is always possible. So let's rewrite these into slope-intercept form. So we have y is greater than -x plus 3, and y is less than -x minus 1. So you can see here that if this were a system of equations, it would definitely be no solution because those two lines have the same slope, so they never cross. However, that doesn't necessarily mean it won't work for a system of inequalities, so you do have to graph. So our first line will be in red, our second line will be in blue. So for our first one, it will look something like this, and it is dotted. And for our second one, it would look something more like this. Same slope, but it has a different y-intercept. So the first equation says y is greater than, so it would be everything above this line. And the second one says y is less than, so it's everything below our blue line. So you can see that there's never any overlap in the shading, which is why this system has no solution. So just look out for that. It is a possibility. It's also a possibility to have what's called an unbounded solution set. So in the first example that we did together, we were able to kind of box in our answer. We knew that there was a boundary on all sides, but that's not always the case, and that's perfectly fine. So let's see what this looks like. So we can rewrite in slope-intercept form for both. So we would have y is greater than -1/2 x plus 3/2. So you end up having something that looks like this. So red and blue. So our first one has a slope of -1 and a y-intercept of 3. Our second one has a slope of -1/2, but a y-intercept of 3/2. So it looks more like this. So they do cross at some point. And this says to shade everything below the red and everything above the blue. So the overlap in shading will occur in this region. So you can see that it's going to keep going to the left infinitely, and so that region is unbounded. But that is our solution set, and we can still find our point of intersection. So we can still find this vertex of our unbounded solution set. So let's do substitution here. Since they're both equal to y, we can set them equal to each other. So we can say -x plus 3 equals -1/2 x plus 3/2. Let's clear our fractions by multiplying both sides by 2. And then here we have -x equals -3, so x equals 3. And if you substitute that into this first equation, oops, sorry, I erased the answer. If you substitute into the first equation, you get y equals -3 plus 3, so y is 0. So you can see it's this coordinate right here, 3, 0. So that's what it would look like to have an unbounded solution set. Okay, go ahead and pause the video and give this problem a try. Okay, so here we have a parabola in red where you're shading everything above, and then we have a linear equation in blue where you're also shading everything above. So the overlapping area is here, but you can see it's unbounded. It's going to keep going up forever. But you still need to find the 2 coordinates of the vertices. So I used substitution. I said x squared equals x plus 2, and I solved finding my x values and substituting into the first equation to find the y values. So we have -1, 1, and 2, 4. So you can see part of this is graphing, but then part of it is just solving algebraically, which is what we've been doing all chapter. All right, so the last thing we're going to talk about are 2 different types of application-based problems. So one of them is consumer surplus and producer surplus. So we've worked with supply and demand functions, and actually we've worked with this exact set of supply and demand functions. So here we have some video game, and this top one is our demand function, and this bottom one is our supply function. So what we did in the past was we found the equilibrium point. So I'm going to first sketch out what this would look like. So I'm going to just focus in quadrant 1 because this is a real-life example. Your x value represents the number of units to produce, and you're never going to produce negative units. The y value represents the price of the unit, so you're never going to have a negative price. So that's why we're only focusing here. So this demand function, which I'm going to do in red, it has a negative slope and a y-intercept of 180, so it looks something like this, more or less. It's a very, very, very rough sketch, but we know that this is 180. Now our supply function has a positive slope, but it has a lower y-intercept, so it looks something like this. Once again, very, very, very rough sketch, but we do know that this value is 90. So what we have done in the past is we actually found this point, which is called the equilibrium point. So you can actually do this using substitution. You can just say this equals this, and you can solve for x. And this is actually in a previous video. We used this exact same supply and demand function or set of functions. So that equilibrium point actually occurred at 3 million and then 150. So the equilibrium number of units to produce was 3 million, and the equilibrium price to set it at was 150. So that's that coordinate where they intersect. Now notice for this problem, we don't want to know what is the equilibrium point. We want to know what's called the consumer surplus and the producer surplus. So this is actually going to occur at in a very specific region. So the first thing you're going to do is you're actually going to make a horizontal line that goes through your equilibrium point. So we know that this line is just y equals 150. And our goal is going to actually be to find the area of this shaded region, which is going to be your consumer surplus. And then we're going to find the area of this region above your supply function, but below that equilibrium line, and that's called your producer surplus. So just in general, this is definitely more of an econ concept, but the idea here for producer surplus, there's all of these producers that are actually willing to produce the video game and sell it at a lower price, but they're actually selling it at this higher price of 150. So all of these people would have been willing to sell it at lower, but they end up getting more money. So that's actually producer surplus. And then there's all of these consumers that would have been willing to pay a higher price for the product, but actually ended up paying a price of 150, which is the equilibrium price. So all of those people that would have been willing to pay more but didn't have to, that would be your consumer surplus. So we're actually going to find the area of those two triangles. And of course, we know there is a formula for area. It's just 1/2 base times height. So let's start with our consumer surplus in red. So our base of our triangle is just the distance from here to here, which is going to be 3 million. And then our height is just going to be the distance from here to here, which you can see is just 30. So then if you do 1/2 times 3 million times 30, you get a consumer surplus of $45 million. So that's our consumer surplus. And now we can do the same general thing for our producer surplus. So 1/2 times the base, which is also 3 million, times the height, which is the distance from here to here, which is 60. So the producer surplus is going to be $90 million. So you have it. So remember, in the past, we've worked with the same exact example, and what we were focusing on before is that equilibrium point. So what is the ideal number of products to produce, and what's the ideal price to set it at? But now we're focusing on this consumer surplus and producer surplus, which is just going to be the area of a shaded region. So just plot out your points. You do need to find that equilibrium point, but then from there you can kind of just set up your 1/2 base times height to find the area of the triangle. All right, so go ahead and pause the video and give this one a try. And note, this one does say 0.00003. Okay, so here's our graph. So you can see that the first thing I did over here was I found this equilibrium point. So I did that using substitution. Since they have the same price, I set them equal to each other, and I solved for x. So x was 1,500,000, and then I substituted that in here to find p, which is 537. So the ideal number of products to produce is 1,500,000, and the ideal price to set it at is 537. But there are definitely consumers that would have been willing to pay more, but ended up only paying 537. And there were also producers that would have been willing to sell it and produce it for less, but got more money. So we have to find those two surpluses. So you can see that for both problems, the base of our triangle is going to be 1,500,000, which is just that distance, your x value. And then you can see that the height for your consumer surplus is just 30, the distance between those two. And the height for your producer surplus is 45, the distance between those two numbers. So your consumer surplus should be 22,500,000, and your producer surplus should be 33,750,000. All right, so this last example, we're going to be creating a system of inequalities. And this is actually going to start to tie into what we're going to learn in the next section. But it's a really nice example to help tie it all together. So this says, the liquid portion of a diet needs to provide at least 300 calories, 36 units of vitamin A, and 90 units of vitamin C. So this is our daily minimum requirement. So we're going to get some of that from dietary drink X. So a cup of that drink provides 60 calories, 12 units of A, and 10 units of C. And then some of it will come from this dietary drink Y. And a cup of that provides 60 calories, 6 units of A, and 30 units of C. So they would like us to write a system of linear equations that describes how many cups of each we must drink to meet the daily minimum requirements. So let's define our variables. X is going to be the cups of drink X, and let's call Y the cups of drink Y. So since there's 3 things that have daily minimum requirements, we're actually going to use that to make 3 different equations or inequalities. So there's one for calories, there's one for vitamin A, and there's one for vitamin C. So it says that we have to have at least 300 calories from the drink. So when you add up whatever you get from X and Y, it must be greater than or equal to 300. Now, drink A will provide 60 calories per cup, so we could say 60X. And then it says drink Y provides 60 calories per cup, so we'll say plus 60Y. Now let's look at vitamin A. So the daily minimum requirement is 36. So when you add them up, they must be greater than or equal to 36. So drink X provides 12 units of vitamin A. And drink Y provides 6 units of vitamin A. So we could say plus 6Y. And then our last one, so vitamin C, we have to have at least 90. So greater than or equal to 90. Now part of that comes from drink X, which provides 10 units of vitamin C, so 10X, and drink Y, which provides 30 units of vitamin C. So these are 3 of the inequalities, but then we also have to remember that this is a real life problem and we're trying to figure out how much of drink X and Y to drink. So we can't drink negative cups of either of them. So we know that X must be greater than or equal to 0 and Y must be greater than or equal to 0. So this is actually the set of the system of linear inequalities. Now this next part is really tying into next unit. So it's actually kind of a bonus for right now, and it's probably going above and beyond what we need for this section, but I do want to take some time to go over it. So if you actually graph this system, remember we're just going to focus in quadrant 1 because it's a real life problem, so X and Y can never be negative. If you graph these, it ends up looking something like this. So that calorie equation, which I'm going to graph in red, would look something like this. The vitamin A equation looks something like this. And the vitamin C equation looks something like this. So remember, our solution set is for all of those, we're shading everything above. So it's just going to be a large unbounded set, but like this. So all of this area right here. So this is what our solution set actually looks like. So these are the different ways where we could consume different amounts of X and Y and at least meet our daily minimum requirements. So for this, we could still go through and we can find these coordinates. So here's one of our coordinates. Here's one of our coordinates. Here's one of our coordinates. And here's one of our coordinates. So we're going to actually be solving different systems of two equations, or maybe even just finding what would be a y-intercept or an x-intercept. So let's start with this one. This is our blue line, so it goes with our vitamin equation, and you can see it's our y-intercept. And the y-intercept occurs where x is equal to 0. So let's take that blue equation and set x equal to 0. So you can see this occurs where y is 6. So we have the coordinate 0, 6. So that's right here. Now let's look at this green one, since it's the next easiest one you can do. So you can see it's our vitamin C equation, and it's occurring at our x-intercept, so which occurs where y is equal to 0. So I'm going to take our green equation and set y equal to 0. So 10x plus 30y equals 90. Substitute y for 0. So 30 times 0. So x will equal 9. So we have the coordinate 9, 0. And then if you look at this coordinate right here, we can see that it's the intersection of our calories and our vitamin A. It's intersection of the blue and the red. So we can actually solve using a system of equations here. So let's imagine we take our red equation, 60x plus 60y equals 300, and we're going to multiply our blue equation, let's say, by negative 10. So negative 120x minus 60y equals negative 360. So now we can solve for x. So we have negative 60x equals negative 60. So x will equal 1, and if you substitute that back in, we get y equals 4. So this coordinate is 1, 4. And then for our last one, you can see that we have the intersection of red and green. So let's keep our red equation the same here. And then for our green equation, we can multiply it by negative 2, so negative 20x minus 60y equals negative 180. So we get 40x, let me scroll down, equals 120. So x will equal 3, and then if you substitute that in, we get y equals 2. So that's going to be our last coordinate. Now, like I said, this problem, they actually only asked us to create the system of equations. So these 5 equations represents our system. But this is something we are going to be doing, so I just wanted to introduce it now. All right, so here's the last example. So see if you can create a system of equations that would describe how to meet the minimum daily requirements for these nutrients. And then if you want, you could try graphing it and solving for the vertices as well. All right, so here you can see that we would call X the number of brand X cups or whatever, however much of the nutrient we would use, and Y is going to be the brand Y nutrient. So there were 3 things that we had to account for: nutrient A, nutrient B, and nutrient C. So we have 8x plus 2y must be greater than or equal to 16, x plus y is greater than or equal to 5, and 2x plus 7y is greater than or equal to 20. So these were the minimum requirements. This is the amount that brand X provided, and this is the amount that brand Y provided. And remember, we have these 2 equations as well, just because there's no way to have a negative amount of a nutrient. because it's just a real life application problem. So if you graph them all, you end up having something that looks like this. So you can set up different systems of equations to find those intersections, but you also want to find the intersections with the x and y axis as well. So like I said, for now, make sure you really understand how to set up the inequalities, but we will be solving larger problems like this in the future. All right, that is all for today. Thank you for watching.